Okay, morning everyone. Okay, so firstly with the midterms, I think you haven't got the results back yet, right? So I think Junheng will give you the results on Friday. Had a look at the marks. They're actually pretty much split. I think there's a bunch of you who found it okay, and then there was a bunch of you who found it maybe pretty hard. So today I want to finish off this chapter, but we can also talk a little bit more about the midterm and do any revision on any topics that you might like me to go through. So should I just first finish off this, and then we can get on to some of the other revision type topics. Okay, so all right, so let me. Right. Okay, so just to recap a bit, so we're talking about energy in this chapter, especially kinetic energy and work, and so I think we all know what energy kind of is, roughly, intuitively. Make this analogy with energy is something like money in a bank account. Kinetic energy, half mv squared, probably you've seen that before. And work is basically associated with the kind of energy transfer due to some force. So basically there's always a work associated with a force, right? So in this case, Bob is pushing this crate here, and so there will be work associated with that if he actually manages to move it through some distance. So there's the work done by Bob on the crate, and I think one of the questions in the midterm was sort of getting to this point that if there's multiple forces on something, then there's different amounts of work associated with each force, right? So each force has a different kind of work. Okay, so basically the concept is that this work is like some kind of transfer of energy, and so we can think of the work as being the amount that's transferred as opposed to the money that's just sitting there in an account. Likewise, some object has some amount of energy, and then there's some transfer of energy. And that's basically what we're talking about with work. Basically, the main formula that you need to know here is that work is force times distance. So you can derive it from just these two equations, F equals ma, and one of the equations of motion. Depending on the direction of the force and the actual movement, work can be negative. Like in this example, when the force is, say, to the right here, and then the actual movement is to the left. You can also do zero work if you don't actually move anything. This is actually vector quantity. The force is a vector quantity, so that means that actually more generally it's a dot scalar product like this. So if there's a force, and then the direction of the movement is kind of different to that, then what you do is you take this scalar product. So this is basically another example of that. So it's some object that's confined to move on this wire, and then there's a force in some direction. And so the work, the only component of the force that contributes to the work is the force that's actually parallel to the movement, right? So because this thing's moving in the x direction, actually only component of the force that matters is actually the force in the x direction. This force in the y direction, this way, doesn't really matter. So it's basically, you can think of it also as scalar product, but you can also think of it like the x component of the force is F cos theta, and then the displacement is d. Yeah, so if there's more than one force, then there's kind of also more than one work. But if you want to find the total work that's done on the object, then you would add the work for each force together. Alternatively, you can just view this force as sort of a combined force, add the forces together, and then calculate the work after that. And yeah, and this is sort of a central result of this chapter, which is basically saying that the kinetic energy change is equal to the work that's done on the system. So if you do some amount of work on the system, then the kinetic energy changes by that amount. And the analogy, the money analogy, is that the work is the amount that you transfer. So, of course, the change in the bank account of Bob here has to be equal to the amount that has gone into his account. So it's obvious from a kind of money perspective, but basically that's the thing that the kinetic energy theorem is saying. Yeah, so I think this is where we got up to last time. Yeah, so yeah, we did this. Yeah, we did this one. Yeah. So, so what if the work, or sorry, what if the force that you are applying is actually changing during the duration of the movement? So, for example, we could have the situation where, again, there's this guy that is pushing on some box like this, and he's applying some force. It's going to go through some distance like this. So if the force was constant, then it would just be work is force times distance. But what if the force isn't constant? What if he's pushing it? Sometimes it's pushing harder, and then it eases back. It's not a constant force. Okay, so in that case, you basically take the integral of the force, and so if you had a graph of the force as a function of distance, so in this example, what's happening is that at the beginning, this guy is pushing with a smaller force than towards the end. So he's gradually sort of increasing the force as he's pushing this box, right? So the reason why it's an integral is you can think of it as, well, at the beginning, or say, let's just look at not this whole interval here, but just a small interval going from, say, this point to some small position later, right? So in that region, we can roughly say that the force is, equal to this value here, right? This value here. And then, if the force is not changing so much, then for that small interval, we can say that it's just force times distance as usual, because that's what we're saying here. And then we can move on to like the next region where the force is increased a little bit, and then we can also do force times distance there. And so you can kind of see that basically what this is doing is it's finding the area under the graph of this force times distance, force versus distance graph. That this area under the graph here is basically the work, right? And we know how to calculate the area under a graph, and that's exactly, you do an integral, right? So basically this is why, this is the more general case of what the work is as a function of force times distance. Of course, if the force is a constant, then when you do this integral, so this is like the initial and the final position. If so, could you do the F2, please? Actually, it didn't change. Can you do it again? Yeah. Change it. No. So now changing the page. So, 2. Oh, I know. Okay, sorry, it's F1 for today. Yeah, sorry, I changed some settings and then, yeah, okay. Yeah, so for some reason I was having problems today and I used a different one, so. Okay, so, yeah, so if this is the general formula of force times integral force with respect to distance, but if the force is actually constant, then we can take it outside the integral. And then we get that. And then the integral just, like this is a 1 here basically, right? The integral of that is just x final minus x initial, and that's the displacement, and so that's force times distance, right? So of course it's consistent with the usual formula for work. This is just a more general case. Okay, so now you might think that this work kinetic energy theorem is a bit trivial. It's like, okay, so like with the money in the bank account thing, it's, okay, so the work that goes in changes the energy. Okay, so it seems pretty obvious. But you can actually use it in some fairly creative ways that means that you can actually sort of shortcut some calculations, right? So let me give you a kind of an example of this. Okay, so the thing with this work is that if this force is not constant, then evaluating this integral is actually, often pretty hard. Nobody wants to evaluate an integral, that's some complicated function that requires some calculation. If it's a, simple function, then okay, you can integrate. But what if, it's some complicated function, you have to do some kind of numerical thing to figure it out, right? So let's, and this is where the kinetic energy theorem actually really sort of shines, if you like, because you can actually bypass that calculation of the work, which is actually often pretty hard, and calculate things in a much, much easier way. So just to give you an example of this, let's consider two guys, again, pushing a box. It's our favorite example for this chapter. So there's steady bob. Is my pointer gone? No pointer. Oh, okay, here we go. Here it is. So there's steady bob here. And steady bob is a guy that is a straightforward guy, just pushes the box with a constant force across the room. So sort of just, has the same force for the whole time. And so the work in this case is nice and easy. It's just force times distance, as we've been saying. Now, let's also say that there's another guy, Crazy Bob, who is pushing with a force, but it's changing all the time. He's pushing hard sometimes, he's pushing soft, he just doesn't push at all for a bit, and then he pushes a bit, right? So, for example, this is the force times position graph, right? So you can see that if you were to try and calculate the work for these two guys, well, the steady bob one it's easy, it's just force times distance. But this thing, what you'd have to do is you have to calculate the area under this curve, and if it's not a nice curve or anything like that, it's actually not so easy to calculate, right? But so in principle, this work thing, if you're given just the force, it's actually pretty, might be actually pretty hard to calculate. But say you also knew the initial and final velocities, right? So say you knew that, for example, that the initial velocity was VI and the final velocity was VF, right? And then actually what the work kinetic energy theorem says is that actually you don't have to calculate work using this complicated formula. Actually, you can just calculate it from the kinetic energy. So whatever your bizarre force function is, it doesn't really matter, because all you have to do is just calculate the difference of the kinetic energies. And if you know what the final and initial velocities are, that's easy. It's just half mv squared, difference. And no need to calculate the this complicated integral. So this is sort of the where this theorem is actually very helpful, right? It gives you another way to calculate the work, which potentially is quite complex, but from an energy perspective, the kinetic energy perspective, can be actually very easy. Let me sort of spell it out for you a little bit. So now let's consider sort of a situation like this. So now we've got Steady Bob and Crazy Bob now pushing with the crate towards each other, okay? And basically what's going to happen is that, so they start with the box stationary, and then, they're both pushing. It's like a push of war. Instead of a tug of war, it's a push of war, okay? Now, in fact, maybe I should have just done a tug of war, because that's actually a real life example, but okay, it's a bit more in line with whatever we've been talking about like this. Okay, so basically what happens in this push of war is that eventually Steady Bob wins, and again it comes to a standstill here, okay? Now, okay, so let's just go through whatever these formulas are. So let's write down the formulas for the work done by Steady Bob in this situation. So what would be the work done by Steady Bob? So Steady Bob is applying force F, Crazy Bob is applying some force function Fc of x. So what would be the work for Steady Bob? So first, I'm just asking for the formula. So just the general formula. If you got the force and goes through by distance, what's the work? Yeah, just FD, right? So in this case, work by, Steady Bob is F times D, right? Okay, what about, so this is going to be Crazy Bob. So what about the work done by Crazy Bob, given that the function is this Fc of x? So, no reasoning, just what's the definition of the work? Well, okay, let me give you a hint here. Well, in fact, it's just right here on the board. You just do the integral of whatever this force function here is. Right? Okay, so do the integral Fc of x. I don't know what this function is, but this is how you would calculate it, right? So, and then, x, let's say that it starts at 0, goes to d, yeah? So it would be something like that. Now, what's the work done on the box if the initial and final velocities of the box are 0? So basically it comes to, starts off still and then it ends up still, right? So what's the work done on the box in that case? Okay, so how about we step it back a bit then. What is the change in kinetic energy of the box?
Zero.
Yeah, 0, right. So the change in kinetic energy is 0. And this work kinetic energy theorem is, if you're applying it to the system with the box, so this is actually like the total work done on the box, right? So individually, what's going to happen is that, so Bob is doing, Steady Bob is actually doing some work. Crazy Bob will he'll also do work, might be negative. But then, in terms of the box, the change in kinetic energy of the box is actually going to be sort of the sum of the work of those two. And so the work done on the box will be 0. And I think you can understand this from the perspective of the bank account analogy. Essentially, in this case, the energy. So just it's a bit confusing with so many Bobs, but in this case, the box is this guy, right? And then so the initial energy of the box is 0, and the final energy of the box is 0, right? So you can deduce that the amount of energy that's gone in or out has to also be 0 because the energy didn't change, right? That's basically what I'm saying. So this is the kind of the total work done on the box. So what can you say about the answers in A and B? So we know that, so this is the total work done on the box. So this actually must be this one plus this one, right? Because there's two forces on the box. Bob is this steady Bob, he's applying force. Crazy Bob also applying force. So those two forces each contribute to some work. And then the total of that is basically, the change in the energy bank account. So, okay, so from this, what can you say about the answers in A and B? What can you say about these two? Yes, they're equal in size. What about the signs of them? Yes, so they're opposite. So, which is going to be positive and which is going to be negative? Yes, yeah. So because this guy's moving this way, force is also this way, so this is going to be a positive thing, right? This thing is going to be negative. And so what we've actually worked out is that FD, so FD plus this integral of this thing is equal to 0. In other words, this thing is actually negative of FD. Okay, so I'm basically just reiterating what I was trying to say before, but see, we've actually deduced something pretty non-trivial, if you like, because as I was saying, calculating this thing is in general hard, right? But we actually, using this kinetic energy work theorem, we can say that, well, whatever this integral is, it's actually just equal to the negative of FD, and this is something we can easily calculate, right? So, so basically it gives you another kind of relation between the work from a kinetic energy perspective that allows you to bypass calculating this weird integral, and it's just always going to be the negative of FD, well, at least for this example. So this is why it's kind of a useful relation, even though it looks kind of trivial, but actually can be useful to deduce certain things. Okay. Okay, so we'll come back to sort of this general idea. So I hope that makes some sense to you. Okay, so let's look at a couple of other types of examples where you've got this work. So one common example is the work done by a gravitational force. So, of course, so there's force of gravity. So let's say there's some object here. Where is it? Here it is. And suppose you are lifting, say, this object here, right? So the displacement is up, but because gravity is always down, force of gravity is always down like this. Okay. So, sorry, I think this is not a lifting example. This is a throwing something in the air example. Okay. So the initial kinetic energy is high here, and then it slows down as you go higher. Yeah? And so if you calculate the work done by the gravitational force, in this case, the force in the distance of displacement is moving in the opposite direction, right? So this thing is going to be a negative quantity because the force is down and displacement is up, at least for the upward leg of the journey, right? So the work is, again, force times distance, or, well, in the case that there's some angle that it's moving, so, if I'm throwing this like this, then there'll be some angle of the movement, right? And so in that case, there'll be an angle of cos theta there involved. So that in this case, the displacement will be at an angle, and then force is always down like this, and so you calculate the work just by, again, taking this scalar product here. So when it's rising, as I said, it's negative, and from a kinetic energy perspective, that makes sense, and work kinetic energy theorem. Basically, the work done by the gravitational force is negative, so the kinetic energy bank account will go down. Yeah. So so the kinetic energy bank account has gone down, because its work was negative. Now, when it's falling, so when it's on the downward leg, then the force and the displacement is in the same direction. It becomes a positive quantity. Of course, falling things speed up, so the kinetic energy bank account will now increase, right? So positive work is done by the gravitational force in this case. Okay, so that was throwing something in the air. What about lifting something? So if I'm lifting something, then there's actually two forces on it. There's the force from my hand pushing it up, and there's also a force of gravity always down, right? So actually there's two forces on it. So there's actually kind of two works, if you like. Yeah. Well, so there's total work, but then two individual works. One is the force, is the work done by gravity, and one is the work done by me, who's like, say, lifting it, right? So in this case, so say I'm going to lift, right? Okay, so I'm going to go from this down. Sorry, is this right? Upward displacement. Oh, sorry, yes. Okay, so this one is lifting, upward displacement. It's going up. This is the gravity down, and this is me pushing up. Right? Okay, so in this case, if I'm lifting this thing, then the work done by gravity is negative. That's just the same as what I just said in the previous slide, because the directions of the gravity and the displacement are opposite. But the work done by me is positive, because the force and the displacement is in the same direction, right? And eventually the amount of kinetic energy change of this thing is actually the sum of those two things, right? There's two forces involved, so there's two works, and then the total work done on the system is the sum of the two works. Don't know how to say that grammatically correct, but anyway. And then the kinetic energy change is the sum of the two works, right? So, so for example, in this case, what am I going to do here? Okay, no. Okay. Yeah, okay, so, and then if I'm going down, it's basically everything is the opposite, right? So now let's look at a kind of a particular example of this when I'm going to start this stationary, and then I'm going to lift it, and then I'm going to leave it there, right? Okay, so that's the process that we're going to think about. So it's stationary here, it's also stationary here, okay? So what's the kinetic energy of the pen when I'm down here? Not moving. Velocity is 0. So kinetic energy is what? Yeah, also 0. I finished lifting. Velocity is 0. So kinetic energy is what? Zero. Okay. So kinetic energy here was 0. Kinetic energy here was 0. So what's the change in kinetic energy? 0, right? So there's actually no change in kinetic energy. Okay. So the total work done on this is equal to 0, right? Now, if you think about how the forces are when I'm pushing on this thing, right? Now, we've said that like there's two forces on the object. There's the gravity that's pushing down, and then pulling down. And there's my hand that's actually pushing upwards, yeah? Now, actually, this is a lot like the crazy Bob, steady Bob example, because gravity is just always like a constant force, just always pulling down. Basically, it doesn't really matter what you're doing, it's just pulling down. Same force, well, so long as the mass is not changing, it's the same force on the object, right? Whereas the way that I push up on this thing is actually pretty, it's not really steady at all, right? Like, my hand, if you try to measure the force that my hand is actually actually applying on this, actually you would find that my hand is like, if you blew up this image here, like with a microscope, you would see that my hand is like jiggling like crazy, right? Because basically, I can't, I'm not a machine. I can't like apply a constant force. And furthermore, I'm going to start with this stationary, and so I'm going to like be applying a force that's firstly to sort of get it going, and then when I've hit steady velocity, then I'm going to sort of ease back on it. Well, it's so light that I can't really notice that I'm doing this, but that's basically what I'm doing. I'm applying force, and then I'm going to come to a stop here. So if I were to actually like plot what my force is doing there, F1 please. So to get it going, I'm applying some force. Well, okay, so right at the beginning, it's just say something like this, and then so this is to sort of counteract. So this is going to be plus mg. And then what I'm going to do to sort of get it going is to apply a bit of a force to try to get it going. Okay, I'm going to ease back on it like this. And then up here, I'm going to slow down a bit so that, so it's going to come to a stop. So, and then I'm going to do something like this. So this is, if you measured the force of my hand, it would look like this, right? And then, sorry, the D would be somewhere over here. And then if I were to say I want to calculate like how much work I did to raise this, what I'd have to do is I'd have to calculate this area under this graph, right? Well, you're going to have to get a computer to calculate the area under the graph of that, because look at how jumpy my hand is. It's like it's not constant at all. So basically, in this situation, I'm kind of this crazy Bob character that's applying this force, but it's so erratic, and it's actually very difficult to, apply a nice, clean, steady force, because, it's just, flesh and bone. And so, but the thing with this, again, is that we don't have to calculate that integral. We know that actually the total work done on the system is 0, and this one we can calculate super easily, right? The force of gravity is just always down, and the displacement is just whatever you measure. So in fact, I don't have to calculate this nasty thing at all. I know that that's exactly the negative of just force times distance, raising it. So mg times d. Okay, makes sense? Okay. So just to finish off this chapter, another small topic, which is force due to a spring. Sorry. So probably a lot of you have seen this. Who's seen this before? Hooke's law. No? Really? Yes. Yeah, probably. I'm guessing everybody's seen it. No? Has somebody not seen it? Okay, you haven't seen it. Okay, fine. So Hooke's law is basically the force due to a spring. So you've got some spring here. Now spring you can elongate it, or you could compress it, right? Either way. And what you notice about a spring is that at the beginning when you're pulling on the spring, it's not so hard to push it, right? But as you're stretching it, actually it gets harder and harder and harder, right? So that actually, by the time it's stretched out, actually you got to really pull on it very hard in order to stop it from snapping back. Likewise with compressing it, at the beginning it's easy, but then it sort of gets harder and harder. And there's, again, a kind of phenomenological law that Mr. Hooke found, which is that the force is actually proportional to the distance. So just the amount of force that you have to apply to sort of counteract the spring force is just linear with the displacement. So this x is talking about how much you're moving it from the steady, or what do you call it? Well, relaxed position of the spring, right? So this is the sort of equilibrium position, if you like, and then you move by x, then this is the force, and there's a negative sign here because it's opposite to the direction that you are moving it. So you've moved it in the positive direction here, but the force is in the opposite direction, it's negative. Likewise, if you're moving it in the negative direction, the force is actually positive. Okay, so for that situation, work done is not just force times distance. It's not, sorry, this should be times, not question mark. So this is not force times distance. Some formula, half kx squared minus half k initial squared minus kf squared. So why is this not force times, just force times distance? Like, if I did force times distance, it would be something like, well, in this case, the distance is x, right? Force times distance would be minus kx squared. Okay, it's something like that, but it's got a half there. So, how do I get that half? Why is it a half? Yep.
The x here is the displacement, right?
Right, yes.
Use x.
Yes. Right, so you mean, so you mean like you need to use this kind of integral? No? Okay. Then, yeah, but, so what do you mean exactly then?
Like
yeah.
This one.
Yes.
I just want to clarify.
Oh, right. Oh, you just want to clarify. Yeah. Yes. So, well, yeah, because the x is the displacement, because x is the movement that you are pulling through, right? So that's the displacement. Now, it's not just force times distance, because this force is not a constant. This force times distance formula, you can only use it if the force is just a constant. And actually, this force is changing. As you pull it, the force actually is getting bigger and bigger. So this is where we have to use our more general formula for force, which is the integral of force times distance. Okay, F1 please. So we've got to use this formula. And so if we stick in, so the initial x and the final x are like this. And then so that means we're going to substitute our formula minus kx to here. And so what integral of x what? Yeah, x squared over 2, right. We do that. So half minus k do kf squared minus ki squared. Yeah, so that's how you get this relation there, basically by putting it into the more general force work formula, which is integral of force times distance. And so we can work out a couple of basic facts, I guess, about the work done by springs. So that's the formula, but let's see what this says. So that work is positive if the block ends up closer to the relaxed position than it was initially. It is negative if the block ends up further away from x equals 0. It is 0 if the block ends up at the same distance from x equals 0. So, okay, mathematically speaking, you know, what this is saying is that the block ends up closer to the relaxed position. So it ends up closer to the relaxed position. That basically means that this x, well, the magnitude of x, right? So the size of x here, xi, is bigger than xf. Yeah, thanks. So, let's visualize it a bit here. So we've got that, and let's say that this is the relaxed position. So that's sort of x equals 0. So let's compare it when. So say it's going to go from here to here, okay? So this is when, so this is the x initial and this is x final, okay? So, well, let's look at it first mathematically. So if xi is basically bigger than xf, then, well, obviously, so we can rewrite this as something like this. So if xi is bigger than xf, then this is positive, right? So that's what the maths is saying. Now let's look at it more from a physics perspective. So in this situation, like, this is the equilibrium position. Which way is the force, spring force, at this position? Right. Well, no. So you got this spring here. This is like the relaxed position, right? So to go here, you're actually stretching it, yeah? So maybe you're thinking of the force applied by you, but actually what we're talking about here is the force by the spring, right? So over here, like, which way is the spring force? Yeah, left, exactly, yeah. So here's the spring force here. Over here, which way is the spring force? Stretching even more, right? Yeah, also left. Actually be bigger than this one, right? So this is that way. Okay, so, you know, at the end it's this way, beginning it's this way. Of course, nothing is going to be different in the middle. So force is this way. The displacement is also this way. So just from a force times, well, okay, work is force times distance basically, okay, proper way to do it is the integral, but just we can get a rough idea of whether it's positive or negative just by looking at the directions. So if the force and the distance are the same direction, then what is the work going to be? No, because so if the force is this way, so remember generally work is force times distance, right? And they are, it's a scalar product, right? So if they are pointing in the same direction, so remember like when you do that scalar product, this cosine factor between them, and if they're parallel, the angle is 0, yeah? And these are the magnitudes, yeah? So if they're parallel, so if phi is equal to say 0, then this work is always positive. So basically because the force is this way, displacement is this way, it makes sense that the work done by the spring is positive because they're basically acting in the same direction. So basically this formula sort of makes sense from that perspective. Yeah.
So the K here is the spring constant.
Yes.
Like if it's moving to the left, why is it positive?
Basically because it's the well, yeah, so I think this is maybe the most physical way to understand it is the explanation due to the forces that I just said here, right? So it's moving to the left. So the force is to the left, and the displacement is to the left, and they're in the same direction. Now, the work is basically positive if the force and the displacement are in the same direction. I mean, basically the reasoning, why is that a positive quantity? Well, because basically the force is acting to eventually give the system energy, right? So, the simplest example, the one that we always come back to, is a guy pushing on a box, right? So he's pushing with a force this way, and it moves some distance this way, yeah? So if the force is sort of successful in actually moving in the direction that it's pushing, that then work is done on the box. Basically, work is going to be transferred, energy is going to be transferred eventually to the box. And that doesn't really matter whether he's on the right, pushing left, and he's going to move some distance d. He's still going to give this box some energy by him pushing it, right? So the force and the distance are, if they're parallel, then work is going to be done on the box, and eventually then energy is going to be transferred to the box. So this situation here on the bottom here is basically the same as the spring. Instead of the guy, there's a spring that's pulling on this object. There's a force that's going left, and the spring is successful in moving this object to the left. And so it's going to give this object some energy. And then, so you say that work done is basically positive. Basically because it's going to give the system kinetic energy. Okay, if it's negative, it's going to be negative if the block ends up further away from x equals 0. So basically in this case it's the opposite situation. So in this case the forces are all the same. This is initial, this is final. Displacement is this way. So this time actually spring is always pulling back to the left here, but the displacement is to the right. And now you might think, how on earth, how is this even? How's that possible? Even how could the thing go that way? Well, that situation can arise, of course, if, for example, say I throw this, give it a bit of a push to the right. Yeah. So spring, object on a spring is going to go back, bounce back and forth like this, right? So if I give it a bit of a push this way, then just because it's got some initial velocity, it will, on its forward leg, go to the right. So its movement will be to the right, but the force will always be pulling back on it. And then once it's got here, the spring will take over and then pull it back. And then that second leg is more like just what we talked about. The first leg is this situation that we're talking about here. So in this case, because this xi and xf are reversed, so this is situation 1, this is situation 2. So, well, in this case, xi is actually smaller than xf, right? This one's bigger than this one. That's going to be bigger than this, so that's going to be negative. And that also makes sense in terms of just looking at the work in terms of a force times distance, because force is that way, but the displacement is that way. So they're in opposite directions, so that's why the work will be negative in this instance. And in terms of kinetic energy, this object will be losing kinetic energy because, well, this work is negative. And in terms of this spring, what's happening is that the spring is slowing it down, right? So I've given it some kick to the right here, spring's acting on it, it's going to slow it down, get here, it's going to pull back on it, fly in the opposite direction. So in this case it will be negative. It's 0 if the block ends up at the same distance from x equals 0. So, okay, so if these are same position, then it's 0. Yeah. Yes.
Then why for the formula on the top that there is a negative sign before the 1/2k?
Here?
Yeah, but then the equations down below doesn't have it.
It does. It's just reversed. So if you put this negative sign inside here, so notice this is xf minus xi.
Yeah.
So this one is xi minus xf. So if you put that in there, it's the same as half k. Put that minus sign inside here, everything reverses here.
Both are the standard equations, right? Just
Sorry, what would it be?
never mind. Yeah.
Yeah. So it's consistent. It's consistent. So let's just do a question here. Okay, 3 situations, initial and final positions along the x-axis for that figure there, -3, 2, and so forth. In each situation, some work done by the spring force on the block, positive, negative, or 0. Alright, so let's do A. So if it's -3 and 2, so that's the initial, and this is the final. So is the work done going to be positive, negative, or 0? Positive. Let's see. Okay, so basically, you know, we can just sort of follow this formula. If so, initial is -3, but it's -3 squared, right? So 9 minus 2 squared, 4. So positive. So yeah, 0. So it's positive. Now this is a little bit more complicated situation than what I was talking about over here. So let's just kind of think about that a bit. Just okay. So this is the equilibrium position here. So what's happening is that we've got the spring here. Over here it's kind of compressed, and then we're comparing it to the situation here. So this is -3, 2. So what's going to happen in what we're trying to do here is to work out what the total work here is. So in this situation, which way is the force actually? So it's actually compressed the spring here, right? So to the left or the right? Unlucky, right. So when you're this way, you're extending the spring, right? So it's pulling back, yeah? When you're this way, you're compressing the spring, so the spring is pushing that way. Did you say right or left? Okay, it doesn't matter. Doesn't matter, I forgot. Anyway, so actually the direction the force changes throughout this movement, yeah. So if you were to draw a force position graph, then this way is actually positive, and it'll look like this. This is the force, and when you talk about the work, what you're actually doing is you're actually calculating this area here. And you can see that that thing's positive. This is why you get a positive answer here. But can we think of it a bit more physically? Well, so whatever the kinetic energy here is, so say it's moving to the right here. Now, is the kinetic energy going to be faster over here? Or, yeah, is the kinetic energy going to be more here or over here, where it's at -3 or 2? Sorry? -3 would be faster? No, actually. So it should be faster over here at 2, because basically if you think about, or just think sort of intuitively about it, you're pressing it here, right? So what's going to say you just compress it here. I didn't really tell you what the speed is initially, but let's just say it's 0. Now, if you let go, basically what's going to happen is it's going to go boing, boing, boing like this, right? And it's going to go boing boing like this. Where it goes fast, where it will be fastest is actually 0, yeah, because that's the equilibrium position, yeah. That's where it basically bounces around. So here the velocity would be the fastest. Here, let's say if the velocity was 0, here there's still going to be some velocity on the other side, because basically this is going to bounce between -3 and 3, right? So it's going to bounce like this, and at 2 there's going to be a little bit of kinetic energy there because it's not quite at the 3. So what basically the positive work is telling you here is that actually the kinetic energy is going to be, the kinetic energy change is going to be positive. It's going to have more kinetic energy here than at the beginning. Okay, what about 2 and 3? Second one. Work done by the spring. Initial is 2, final is 3. Yes, negative. So see that from the formula. That's smaller than that, so it's going to be negative. Okay, and if you make some sort of physical sense of it, it's there, and basically it's going to be negative, so it's going to lose energy in going from here to here. Okay, what about -2 and 2? Initial is -2 and final is 2. So from the point of view of the formula, -2 squared is what?
4.
Yeah, 4. 2 squared. 4. 4 minus 4, 0. So this is saying it's actually 0. Now, how to make sense of that? Basically, it's sort of like this. Now, this situation, just adjust to 0 here. So this graph is going to look a little bit more like this. So basically these two, the work in going from here to here and work from going here to here actually cancels. So basically what's going to happen is that in going from here to here, the thing is going to speed up. So work is going to be done on the object. Kinetic energy is going to be given to it. But then going from here to here, actually work is done, negative work is done, which means kinetic energy is taken away. In other words, it just bounces, goes boing, 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 like this. So this is the extreme points of the motion in this case, and the work done on it is actually 0 because it actually kind of cancels out in the forward and in the first and the second parts. And the kinetic energy change is actually 0. Okay, so that's about it. There was one small. Oh yeah, sorry, just to finish off, these are just more or less definitions. So power is basically the rate of the work that's being done. So it's the work divided by the time interval. So if you can also talk about an average power, which is like the work done divided by the time, and so units of power are watts. So I think you've heard of that before, hairdryer, 1,200 watts, something like that. That's the amount of energy per unit time that it's sort of using up. So in this case, work divided by the time, or you could, if the work is kind of changing dynamically in time, then you can also take a derivative, so there's instantaneous power. And in the case of a constant force, you can also have a power relation that looks, so if the force is actually constant, if you take the derivative of this, then it is the force times the velocity. So this is not a very common formula, but you can also work out the power in this way. So because the force is actually just a constant in this case, you can also work out the power by multiplying force times velocity. This is, I wouldn't say this is a very common formula, so I personally don't have that in my mind all the time. But certainly you should know that basically power means energy per unit time, right? So I probably wouldn't expect you to just immediately know power is force times velocity. But I think knowing from this fundamental definition, you can deduce that power is also force times velocity. Okay, I think maybe we'll leave it there. There's a couple of questions there, but okay. All right, so of course the midterm is next Tuesday, so it will be very similar, everything just like the quiz. So the quiz was sort of intended as a kind of a dry run through for the midterm. So for Tuesday, basically, come and seat yourself in this room as you did for the quiz, and if you have any questions that you were concerned about, then please come and see me. I'm in room 1200 from 4 o'clock onwards every day, so you can just jump in and ask me. Your recitation instructor, he's usually also there at the same time, so you can ask any one of us, and you'll probably go through some more questions from the quiz on Friday too. So, okay, so good luck.